Hi everyone. Is it audible now?
Yes, ma'am.
Okay, thank you. So, how was your test yesterday? How was your scores? For nodal students, like we can see the score in our dashboard, but other students, I don't know. That's why I'm asking you. Did you write it well?
Yes, ma'am.
Okay, good. And the thing is that, like, there are some of my students who also joined. I'm so happy that after school also I am able to teach you guys, so I'm happy in that sense. Now let's start our today's topic, that is electrostatics. As you can see, we have completed our 11th topics. Okay, from now onwards we are covering our 12th topics, and I know you have the timetable already, so next all topics are our 12th. Okay, so one thing I have to tell you, if you have any suggestion, like you don't need much theory, you want more PYQs, anything like that is there, you can directly tell me, okay? Or personally message me, say it during the class, or after in group also you can message. So according to that I will make the changes, okay? So for today's class I have prepared as previous one only. We will first do the theory, then go to the like problem solving, not PYQs. Okay, starting, like, which other topics we will be covering today are Coulomb's law, electric field, electric potential and potential energy, equipotential surface, electric dipole. So these are the major topics from which the questions will arise. Okay, electrostatics is a like topic that, even though very limited amount of subject like topics are there in the chapter, there are like multiple ways of asking question, like so many types of questions can be asked from this. That's why, like, practice is necessary, and you already know there are so many formulas in this chapter, so it's better that when you are solving the PYQs, keep a formula sheet with you. Okay, write down all the formulas in the chapter, keep it with you while solving. Okay, so you don't have to by heart it from first, but after solving and solving again, these formulas will be like imprinted on your mind, so you don't have to worry about that. Okay, starting from Coulomb's law, and when we were teaching gravitation, what did I tell you? Like, it is so similar to electrostatics. Any formula in gravitation you can relate to electrostatics. In electrostatic, few extra formulas will be there, that's it. Okay, Coulomb's law is same as our universal law of gravitation. Okay, what does it say? Universal law of gravitation: any two bodies in the universe attract each other with a force proportional to their masses, product of their masses, and inversely proportional to the square of distance between them. So Coulomb's law is force between two charges proportional to product of their charges and inversely proportional to square of distance between them. Okay, and the force acts along this line. Okay, line joining both centers, force acts in that line, same as in gravitation law. And in this, the constant K, there the constant G is gravitational constant, here K is K equal to 1 by 4 pi epsilon naught. Epsilon naught value is this 8.85 into 10 to the power minus 12, and K as a whole we can write as 9 into 10 to the power 9. Okay, so if you have this formula, like majority of questions you can be solved using this, but we need other concepts also. So can we move on to the next topic? I'm audible. Okay, now force, that from equation you will get the magnitude of the force, but we need the direction also, because force is a vector quantity. We need to express it in vector form. So vector form, our formula will become q1 q2, since k is a constant and q1 q2 are what? They are charges and scalar quantities. They doesn't have any direction, and only which thing having direction is our r. So we can write it as r square into r cap. Force will be acting along r cap direction. This line joining them is called as r cap direction. Okay. And will it be attractive or repulsive depends on the nature of charge, positive or negative. Screen is not visible. Which part is not visible, Dheeraj? What I am writing or this figure? All not visible. What about now?
It is visible.
Okay. So, direction we will write as r cap. But this is not just the vector form. Like you can see here, O is the origin. Okay. And two charges Q1 and Q2 are situated at R1 distance and R2 distance from the origin. Okay, which means R2 is the position vector of Q2, R1 is the position vector of Q1. In such cases, how do you express this? So, distance between them can be said to be, let's see, if you have two vectors, R1 in this direction, R2 in this direction, and you need to find a vector joining both of them. So, this is somewhat forming like a triangle of vector addition, right? If let's say this is equal to R, this can be R2 plus R equal to R1, which means R equal to R1 minus R2. If direction of R is this. And if we are taking direction of R opposite to it, okay, direction of R opposite to that, how it will be? R can be written as R2 minus R1. So this is how you find the direction of position vector, okay, distance between two points. So I hope this is clear. It is directly application of triangle of vector addition. So since it is R1 minus R2, we will write as R12. And here it is R2 minus R1, so we will write as R21. R21 and R12 both are same in magnitude, equal in magnitude. Okay, R21 is equal to R12 in magnitude, but their direction is opposite to each other. That is the only difference. Is it clear? Okay. Next is superposition principle. So it is adding upon the vector form. Okay, if you know vector form only, you can like properly apply superposition principle. What does it say? Let's say a charge Q3 is here, then charge Q2 and charge Q1 are also present. So what will be the force on Q3 due to Q1 and Q2? If two charges are present, we know the force equal to Q1 Q2 by R square. But what if two charges are present? Then we have to individually find the force. Force due to 1 on 3, that will be equal to K Q1 Q3 by R13 square, R13 cap. Okay, so it is acting along this direction, and since both are given as positive, we can say that R13 will be acting in that direction. Sorry, F13. Similarly, because of charge 2, there will be force which can be said as Q2 Q3 by R23 square R23 cap, which will be acting along this direction. Okay, so net force on the charge Q3 will be vector sum of these two forces. So F net on charge 3 is equal to K Q1 Q3 by R13 square R13 cap plus K Q2 Q3 divided by R23 square R23 cap. Is that clear? That is vector sum, okay, not like directly adding the magnitude. We have to consider them as vectors and then add. For example, here they have taken like parallelogram law of vector addition, or else you can take x component, y component separately, add them. So two methods are possible: directly find using parallelogram law, or by using like finding components, x and y components, then adding. So in these two ways you can find net force on any charge. Is it clear? Okay. Next is about equilibrium. Equilibrium, I think we already discussed regarding this in one of the previous class. But again, equilibrium questions will come with electrostatics also. That's why I am explaining again. Okay, stable, unstable, neutral equilibrium. Remember it like this. If from the mean position we move a little, it is coming back to mean position, it is stable equilibrium. And if you move from like mean position and it will not come back to the original position, that is unstable equilibrium. Neutral equilibrium means if you move from the position also, it will remain in equilibrium. It will not change much. Okay. Is that clear? Okay. So no further explanation on that. Next we are coming to electric field. Okay. Most of our questions will be related to electric field. Why? Because if you know electric field, you can find electrostatic force and you can also find potential V. So electric field is the like major main character in this show. Coming to electric field, we can simply say that electric field is equal to F by Q, which means electric field is the property of a single charge. Electrostatic force, you need two charges. Electric field, you need only one charge, and the field around it, like the area around it, will be affected by that charge, right? So how is it affected? That is called as electric field. Okay, if you place a unit charge in that area, how it will behave? It depends on the electric field of original charge. So we can find the equation E equal to K Q by R square. Actually, F is equal to, let's say, K Q by R square. In that case, we will write E equal to F by Q. Then you will get this equation. And since electric field is also a vector quantity, its direction also can be said as R cap. And you know that for positive charge, it will be radially outwards electric field, and for a negative charge, it will be radially inwards. How you draw electric field lines? I don't think I have to explain that, right? Okay. Okay, so this is electric field. Do you have any doubts regarding this? No. Okay. So moving on. Once we know electric field for a point charge, Coulomb's law and the superposition principle and electric field which we now described are for point charges, a single charge sitting. Okay. But what if they are like continuous charge distribution? For example, I am distributing charge over this pen. It is not a point charge. So if I take some other point and find electric field, it cannot be from one point. Okay. So we need a generalized equation for continuous charge distribution. For example, for point charge which we already discussed, KQ by R square. If you are plotting it against distance, okay, electric field versus distance, you will get a graph of 1 by R square. Okay. Next one, infinitely long charge. Like you are taking an infinite wire and supplying it with charge, and what will be electric field due to that at R distance? So we are taking a point at R distance, then electric field at that point will be given by lambda by 2 pi epsilon naught R, or here we can substitute with K 1 by 4 pi epsilon naught then we will get 2k lambda by r. R cap direction like radially outwards or inwards depend on the charge. Okay. Same equation, I am telling you, we saw the same equations in gravitational field. Okay. So all these are same equations only. There it will be gravitational like mass and gravitational constant. Here it will be charge and k, that's it. Here since you can see it is proportional to 1 by r, the graph will be of 1 by r. Next, for a infinite non-conducting thin sheet, that's what you should be careful. Like there are non-conducting thin sheet and conducting thin sheet. For example, if you take a plastic sheet, that is a non-conducting sheet. If you provide it with charges, it will distribute along one surface only. But if it is a conducting sheet, like let's say aluminum foil you took and you supplied it with charge, what will happen? It will it will spread over first surface and second surface. Okay, so that is the difference between conducting and non-conducting sheet. And for non-conducting sheet, electric field at any point will be equal to sigma by 2 epsilon. It will not depend on r, distance from the sheet, it will not depend. It is a constant value sigma by 2 epsilon. And what is sigma? Sigma is total charge by total area, that is charge density. Okay, so sigma by 2 epsilon naught is electric field due to infinite non-conducting sheet. And if you plot the graph against r, what will be it? With respect to r, it is not changing, it's a constant, so it will be a horizontal line. Is this much clear? Okay. Next is uniformly charged ring. I hope you have studied that derivation for your board exams, like taking a small element on top, small element on bottom, then at x distance from the center what will be electric field. So this is r radius and this distance is x. So at this point what is electric field, that we will be finding, and the equation is this. Okay, kqx by r square plus x square the whole raised to 3 by 2. Okay, in this electric field at the center of the ring is 0. Why? Because at the center to every direction it is getting equal electric field. So when you add it up, it will be 0 in the middle. Now if you see the direction, okay, direction of this, since electric field like it's positive, let's say it's positive charge, from this side it will be in this direction, from this side it will be in this direction. So both side electric field will be in opposite direction. That's why the ratio is like, the graph is like this. Okay, and it will be maximum at a point r by root 2. How we are finding the maximum? We did a problem before. We are finding differential and we are equating it to 0 and you are finding the value of x. Okay, so you are finding dE by dx, equating it to 0, then you will get the maximum value. Okay, next is infinitely charged conducting sheet. When it comes to conducting sheet, I told you it is distributed over whole surface. So electric field is sigma by epsilon naught. Again it's a constant, so graph will be constant. Next is uniformly charged hollow conducting, non-conducting, solid conducting sphere. So many things are there. There is hollow sphere which is conducting, hollow sphere which is non-conducting, and solid sphere which is conducting. These three have the same equation. Okay, which non-conducting and conducting hollow sphere, conducting solid sphere. Why? Because hollow sphere charge will be distributed over the surface only. So both solid or conducting, it will be distributed over the surface, no problem. When it comes to solid sphere also, which is conducting, for a conductor charge will not go into the volume, it will be distributed over the surface only. So solid sphere conducting one will act as a hollow sphere only. So that's why equation is same. And for outside the sphere and for inside the sphere, we have electric field. Inside sphere it is 0, Outside sphere it will be like a point charge. I hope that's clear. Outside the sphere the equation will be of a point charge, and inside the sphere electric field will be 0. And since it is like that, you can see the graph. From 0 to R there is no electric field. From R it will start from the maximum on the surface, then it will go as 1 by R square graph. Okay. Next one is solid non-conducting sphere. For a non-conducting sphere, charge will be distributed in the volume. For conducting sphere, charge will be distributed only in the surface. So solid sphere, only non-conducting one, we have this formula. For R, outside the point outside the sphere and point inside the sphere. Here you can see inside the sphere also electric field is present, and it is found using KQR divided by R cube. This R is distance to the point, this R is radius of the sphere. Okay, for example, if this is the sphere, R is its radius and small r is the distance to the point. Okay, and since inside also electric field is present, it will vary. Inside you can see it is proportional to R, so it will be linearly increasing, and outside it will be proportional to 1 by R square. So from surface it will behave like a point charge. Okay, all these both outside the sphere it will behave like a point charge. Inside the sphere, for this one it is 0, for this one it is proportional to R. I hope it's clear for all. Okay, everybody is listening, right? I am not boring you guys with so much details. Okay, next is for a finite line charge distribution. In the previous slide we saw for infinite long charge. What if it's a finite wire, like a finite wire, and the charge is distributed over it? In this case what we will do? Okay, in that case let's say this is point and this is distance R, and we can say that this angle is equal to theta 1, this angle is equal to theta 2. Both angles are not same. Okay, in such way if you are taking, there will be electric field along this direction also, this direction or downward direction depending on the answer. Okay, so this is EY and this is EX. Electric field along horizontal direction and electric field along vertical direction. For horizontal direction, EX you can find using this formula. Don't think about the integration part and all, it's not needed. So EX you can find using this formula, K lambda by R sin theta 1 plus theta 2. Now Y component, EY you can find using this formula, K lambda by R cos theta 1 minus cos theta 2. Sorry, cos theta 2 minus cos theta 1. Depending on value of theta, direction of EX and EY will depend. EX will depend on positive or negative charge only. Positive charge, EX will be in outward direction. Negative charge, EX will be this direction. And EY, if this side is more, EY will be in upward direction. If this side is more, EY will be in downward direction. Okay, so so what we were saying is that, like for a finite charge distribution there are two components, okay, EY and EX. If this side is more, EY will be in upward direction. If this side is more, EY will be in downward direction. Okay, similarly positive charge EX towards positive direction and negative charge EX will be towards negative direction. Like that you can find direction of EY and EX, and magnitude you can find using this. Is that clear? Okay, then we can move to the next topic. that is electric potential. Okay, as we told during the gravitation also, electric potential is work done to bring a unit charge from infinity to a point in electric field. So our big charge Q is here, it is having electric field around it. Okay, and to this electric field I want to bring an external charge, that is Q naught. Okay, but Q naught value is 1, and I am bringing this charge to here, point R. From this, what will be work done? So work done equation equal to integral infinity to R F dot dr. This is the formula for work done. But the thing is, Q naught equal to 1, right? If you substitute that in for F equation, you will get infinity to R E dot dr. Okay, so if you do this integral, you will get what is potential, work done, and potential is nothing but negative of work done. So we can say that electric potential equal to minus of integral infinity to R E dot dr. That's why this equation is coming. Actually it is work done only, but when you substitute one charge equal to 1 in force, you will get E dot dr. Force, one charge is 1, so kq by r square will come, and it will come. So it will change to minus integral infinity to r E dot dr. Okay, in this only, like we can say equation for V equal to potential energy by Q also, and you will get the formula that kq by r. This is Q, r is distance which we are bringing the external charge, and V equal to kq by r you will get. Since this relation is there, one opposite relation also there. Like if V is given, how to find E? E is equal to minus dV by dr. This formula also there. If it is x direction, it will be dV by dx. Y means dV by dy. Z means dV by dz, like that. Okay, and if it is in 3 dimension, let's say electric field is a vector quantity, but potential is scalar quantity. In that case, how do we express? Remember during gravitation time I told you an operator del. Okay, which means partial differentiation we will do. Okay, that one. But based on that you won't get any numerical, so it is just for concept knowledge. Is electric potential clear for all? Okay. Okay, next is we have to find the potential for different objects. Same things which we did for electric field. Electric field, whichever objects we found the... Sorry guys, wait 1 second. Okay, so like for whichever objects we found the electric field, for same things we have to find electric potential also. So for point charge which we derived kq by r, for uniform ring, okay, for this at center potential is there, but what we did when we found electric field at the center of the ring was 0, but at center of electric ring potential is present, that is kq by radius of the ring, and at the axis formula of V is there. These we are finding using integration, but we don't want that derivation, we want the final values only. Okay, next is for uniformly charged hollow conducting non-conducting sphere. As I told you, there is hollow conducting and non-conducting sphere and solid conducting sphere. For that, potential inside and outside present. Electric field is not inside it, but potential is present inside, which is a constant value. That's why graph is like this. Constant inside and coming to outside, it will decrease proportional to 1 by r. Okay, is this clear? I think it's working. No. You can close. Hello? Students, is it okay now? Okay. So we were discussing about electric potential. Is these three clear for you? Point charge, uniformly charged ring, and uniformly charged hollow, conducting, non-conducting, solid, conducting sphere. Can we move to the next? Okay. So next is uniformly charged non-conducting sphere. Here inside also charge is present in the volume. So potential outside, it will be similar for a point charge. Potential inside you have to find using this formula or this formula. Okay, first formula everything is direct. R is radius, capital R, small r is distance to the point which we are finding. In second formula, rho is nothing but density, charge density. Okay, so rho equal to charge by volume. That is charge density in second formula. Here also just remember the graph. You won't be having formula based question from this, but remember the graph. Okay, for solid sphere what will be potential variation. Now infinite line charge, infinite conducting and non-conducting sheet. The problem about this is that we cannot find potential at exact one point. Like if you try to find, you won't get an answer, but you can find the potential difference between 2 points. Okay, so in these three cases, individual potential at a point is not defined, but potential difference can be defined. For line charge, it is 2k lambda ln RB by RA. If like you want to find VB minus VA, potential difference between B and A, you can use this formula. Similarly, for conducting, non-conducting sheet, formula will be like this, and conducting sheet, it will be like this. So these are potential difference formula, not potential at a point. Is that clear? Okay. I think the screen is not properly visible for you guys, right? Is it visible? Okay. Okay, it's not. I know it's like we are talking about equipotential surface here. Okay. Why equipotential surface is like potential at constant at a whole surface. That's what is meant by equipotential surface. Just exact translation of that word. So for a point charge, if you take an area around it, the formula for potential is equal to k q by r, right? So at r radius, if I draw a sphere, what will be there? Potential will be same all over the space, because it is only depending on r. So for a point charge, it will have spherical equipotential surface. Okay, and if you take a sheet, okay, as you know, like potential difference will be between 2 points, so it will have like this equipotential surface. Okay, and this is the direction of electric field. Next, if you are taking line charge distribution, like at r distance, 2k lambda by r it's coming, right? So at r distance, what it will be? Constant. So it will have a cylindrical equipotential surface around it. Okay, so these are the main 3 equipotential surface we should deal. One is for point charge or sphere or something, it will be spherical equipotential surface, and for sheet it will be plane equipotential surface, and for line charge it will be cylindrical equipotential surface. And here you can see one thing common for all, that is electric field is perpendicular to equipotential surface. If you take this angle between electric field and that point, surface is 90 degree. Here electric field and this is having 90 degree between them. Here also electric field is in this direction. So electric field and the surface will have 90 degree difference. So electric field is always perpendicular to equipotential surface. One point to remember. Second point to remember, if you are moving a charge, like there is a external charge Q, I am moving it from this point to this point. Since potential is not changing, there will be no work done. If you are moving a charge on the equipotential surface, there will be no work done. But if I am moving the charge from here to here, potential is changing, which means work will be done. So this is the significance of equipotential surface. Is it clear? Okay, now sometimes you will get a question, equipotential surfaces are close to each other and away from each other. When they are close to each other, potential is high, okay, in that region, electric field is more, and if they are away from each other, electric field is intensity is very less. When potential surfaces are close to each other, intensity is high, and when they are away from each other, electric field intensity is low. So that point also we can get. Next is electrostatic potential energy. Okay, this is directly our work done. Work done equal to minus of infinity to r F dot dr. In the previous equation, what we did, we substituted F for unit charge and substituted Q equal to 1. Then it turned into E dot dr. Here we are not bringing a unit charge. So we are bringing an actual charge, and what will be the work done? That will be potential energy U. Okay, and simpler equation will be KQ Q by R, and this can be modified as U equal to V into Q. So for potential energy we will get three equations. Okay, KQ Q by R or V into Q and integral of minus F dot dr. Is it clear? Okay. Why we need this is for next topic, that is electrostatic potential energy of a system of charges. Again, this we did in gravitation also. When we are accumulating all these, how much work we are doing, that is potential energy of the system. So first Q1 is here. Okay, we are bringing Q1 from infinity. Work done will be 0 because there is no electric field in this region. I am just bringing from one point to another. Next, I am bringing Q2 to this point. Okay, so this distance is R. I am bringing it from infinity. Okay, so work done for this will be our potential energy U equation, that is U equal to potential due to 1 into charge Q2. Okay, this will be work done to bring 2 is equal to potential of 1 into Q2. Similarly, if you are bringing Q3 here at R dash distance, this is R1, this is R2, this is R3. Okay, from infinity to this point you are bringing, work done to bring 3 will be equal to potential of 1 into Q3 plus potential of 2 into Q3. Now if you add this total work done, you will get potential energy of the system. Is it clear? Okay, so moving on. For discrete charges, you need to know how to find for individual systems, okay, because based on that you will get question. But for continuous charge distribution, you won't get numerical, but you will need to know this formula, okay. For a hollow sphere, what is the potential energy? That is kq square by 2r. For a solid sphere, what is potential energy? 3kq square by 5r. Do you remember this formula when we saw from gravitation? For a solid sphere, like for earth or something, what is the gravitational potential energy of the system? Same formula. Instead of k it was g, instead of q it was m. That's it. Any doubts? No. Okay. Next is electrical energy density. Here also we directly need this formula only. Energy density is potential energy by volume, okay. Energy density means potential energy by volume. You will get the formula half epsilon naught E square. If you know electric field, you can find potential energy density, that is half epsilon naught E square. Epsilon naught value we already know, so just substitute the value of E, okay. Is there any doubt regarding this? Is it clear for all? Okay. Next we are talking about electric dipole. So from this point onwards, we stop the similarity between gravitation and electrostatics. This is a whole new concept in electrostatics, that is a positive and negative charge kept at a d distance from each other, and both are having equal charge, like equal charge magnitude. Here it will be plus q, here it will be minus q, okay. If in that case it is called as a dipole. Electric dipole, charges of equal magnitude and opposite sign kept at a small distance, that distance is d. For this, a defining component is there, that is dipole moment. We represent it using letter small p, dipole moment, and equation for this will be qd. Okay, if you learned like 2aq, don't remember that equation, okay, because you will simply multiply 2 everywhere. You will get confused or make careless mistake. Distance into charge, that is the equation. So qd is fine, okay. So dipole moment is qd, and since you saw that it's a vector quantity, dipole moment, its direction will be from negative to positive, direction of p, okay. Do you have any doubt in this? Okay. Next one, if we have to find electric field and potential due to this. So basically we are doing this thing only. We will take a system, we will find electric field, we will find potential, then we will find potential energy maybe, then if we will keep in external field, those things only we are doing, okay. If to find electric field and potential, this is the equation for at a general point, okay. At a general point, what will be the value of electric field and electric potential? And like if this is in vector form, this is in like magnitude form, only magnitude if you are calculating for electric field. So there are 2 points mainly. This point is called as equatorial point, and along this line is called as axial point, okay. So from this we can say that direction of p is this, right? This is the direction of p, and electric field at the axial point will be equal to, we have to find this theta. Theta is angle between position vector and p. Position vector in this direction, p also in this direction, which means theta equal to 0. Theta equal to 0, cos will be 1. So 1 plus 3, 4, root 4, 2. So 2 kp by r cube. That will be electric field at the axial point. And what will be the direction? Direction will be same as of P. Okay. If it is on this side, magnitude will be same, but direction will be opposite of P. Direction will also be same as P. Both side electric field direction will be same as of P. Okay. Coming to equatorial point, theta will be 90 degree there. Okay. So E equatorial, theta 90 degree, cos 90 0. It will be root 1. So kp by r cube. And what about the direction? Equatorial point, direction of electric field is always negative of direction of P. Okay. So if you have direction of P, equatorial point, it will be in opposite direction. Okay. Is it clear about electric field? Now coming to potential. On axial point, since it is equal distance from positive and negative, any axial point you take, potential will be 0. Sorry, not axial, equatorial. Any point on the equatorial, potential is 0. And on axial point, divide by r. Like E multiplied with r, you will get V. Okay. V equal to E into r. Simply we can say. So V will be equal to kp by r square. But for axial, you don't have to put that. Equatorial, you don't have to use this. It is 0 there. Okay. Like electric field and potential due to dipole at equatorial point and axial point. Is it clear for all? Only Surabhi is responding. Are others not listening, or like it is confusing for you guys? Okay. Good. So after that we are keeping the dipole in external field. So here we are assuming the field is uniform. Uniform means at every point electric field value is magnitude is same. Okay. Uniform electric field means at every point magnitude of electric field is same. So if you are placing it in this direction, you know that electric field will be from positive to negative. So plus Q will be attracted in this direction with F1 force, minus Q will be attracted to this direction with F2 force. Since E is same, force is equal to Q into E. E is same at both points. Charge magnitude Q1 and Q2 is same, which means force will be same but in opposite direction. From rotational motion, we know that such forces are called as coupled, force coupled. Okay, equal and opposite force acting on the same body is called as a force coupled, and torque due to this will be QE sin theta. Okay, QED sin theta will be torque. And on further we can find that torque will be equal to P cross E or PE sin theta n cap. Formula direction we have to see later, and P can be written as 2 is not there, sorry. Further it can be written as QD E sin theta. So these are the formulas you should know for torque of the electric dipole in external uniform electric field. Okay. Potential energy will be P dot E, that is PE cos theta, or can be said as QDE cos theta. This will be potential energy at any if you keep in any direction. Then if it is changed from one direction to another direction, you can find potential energy change also. Okay, so torque, if you are talking, like if the dipole is kept like this, okay, positive here, negative here, equal force acting in opposite directions, right? So it will not rotate, this will be in equilibrium, but it will be in stable or unstable equilibrium depending on the alignment. Okay, let's say minus q is here and plus q is here. Plus q is attracted in this direction, minus q is attracted in this direction. If I move it little bit from this alignment, it will come back to its original position, right? Which means it is stable equilibrium. Okay, now if plus q is this side and minus q is this side, electric field in this direction, electric field in this direction, then q plus q is attracted in this direction, minus q attracted in this direction. Still it will be in equilibrium, but if I move from this position, it will turn, it will not come back to this position. So this is unstable equilibrium, okay, of the dipole. Is that clear?
Yes, ma'am.
Or do you have any I hope nobody has any doubt regarding this, so we can move on, I guess. Last topic, that is Gauss's law. Gauss's law, you don't have to worry about all the derivations you did for your board exam. Okay, those things we don't need. We need only this formula. Electric flux passing through a closed surface equal to Q enclosed, which means charge inside the total charge inside that surface divided by epsilon naught. And this formula we are using for closed surface, like if there are some charges inside a bottle. So total flux through the bottle will be equal to total charge inside divided by epsilon naught. It does not depend on which shape. Like if I am keeping like Q charge inside a circle or inside a square, like cube, sphere or cube, both will have same flux only. Okay, so it will only depend on charge inside the surface. Is that clear for all? Okay, so after this then we can move on to problem solving, I guess. So before going to that, I will give you guys a link. Please fill that, okay? Because I think after this people will leave. So before leaving, please fill this link. I have posted a link in the chat box. Please fill that, okay? I will give you like 2 minutes. It's a very small form. Once you filled, please give me a thumbs up. Okay. Is everyone's over? Can we resume the class? Okay. I guess most of you are done. So we will resume the class. So starting with this question. The charge on two spheres are plus 7 mu coulomb and minus 5 mu coulomb respectively. They experience a force F. If each of them is given an additional charge of minus 2 mu coulomb, what will the new force of attraction be? So, initially there is plus 7 mu coulomb and minus 5 mu coulomb, right? And distance between them, let's assume it's d, and force between them is F, which will be k into 7 into minus 5 divided by d square. In additionally what they are doing, they are just giving extra charge, they are not changing the distance between them. So new force will be equal to k into 7 plus minus 2 will be equal to 5. Then minus 5 minus 2 will be minus 7. Distance is not changed, it will be d square. See, negative sign just changes from one to another, but we are multiplying the same things, right? Which means its force will be same only. So F dash will be equal to F. Answer. Everybody understood this? Okay. Then we can move to the next question. Nadaf, are you having any doubt or you are unmuted? Okay. The next question. 4 charges Q1, Q2, Q3, Q4 are placed at 4 corners of a square of side root 2 meter. What is the potential at the center of the square? Okay. So if you take Q1, Q2, Q3, Q4 and at the center every charge is having d distance from it, right? So total potential will be V1 plus V2 plus V3 plus V4, which means K Q1 by D plus K Q2 by D plus K Q3 by D plus K Q4 by D. As you can see, K by D is common for all. We can take V equal to K by D into Q1 plus Q2 plus Q3 plus Q4. Now it became much easier. K value 9 into 10 to the power 9. D distances we have to find. So this distance equal to root 2 meter. This distance also root 2 meter, which means diagonal is equal to 2 meters. Okay, diagonal is 2 meters. D is diagonal by 2. So D is equal to 1 meter. So by 1, total charge when you are adding, you will have 2 minus 2, 0. Minus 3 plus 6, 3. So multiplied by 3 into 10 to the power 8. What will be the answer? Minus 8, sorry. Yes, option A is the answer, 270 volt.
Option.
Yes, very good. Everybody understood this one? Can we move to the next question? Okay.
Yes, ma'am.
Next one. There is an electric field E in x direction. If the work done on moving a charge of 0.2 coulomb through a distance of 2 meter, a line making an angle of 60 degree with x-axis is 4 joule. Work done is 4 joule. What is the value of E? So work done is nothing but Q, potential into Q. Okay. And potential we can say as E into E dot distance into charge Q. Okay. This will be written as ED cos theta into Q. This will be work done. Okay. In this electric field we have to find work done is given as 4 joule, electric field not given, D is given as 2 meter, cos theta is given as 60 degree and charge is given as 0.2. Okay, now just find E. Yes, very good. Okay, answer is 20 Newton per Coulomb. Everybody got that answer? Okay, then we can move to the next question. Next one, if the electric flux entering and leaving an enclosed surface is phi1 and phi2, electric charge inside the surface will be. Okay, see, if a surface is here and Q charge is here, flux entering and leaving the surface will be same. Okay, which means here entering and leaving is different, means there is some charge inside. So flux entering is Q1, flux leaving is Q2. Okay, so difference of that will be our net flux coming from inside. Okay, phi equal to Q by epsilon naught, equation also there. So Q is Q enclosed. Okay, so Q enclosed will be equal to phi1 minus phi2 or phi2 minus phi1, we will see later, but still we will get that Q enclosed will be equal to epsilon naught into phi1 minus phi2. Okay,
D
option D. The change in Q1 minus Q2 or Q2 minus Q1 depends on like if it's a positive charge inside or negative charge inside. Okay, is it clear for all? Okay. Next is electric potential V is given as a function of X. V is given. Find the value of electric field at X equal to 1. So what is the relation between E and V? E equal to minus dV by dx. Okay, so just find differential of this equation, substitute X equal to 1, you will get E. This you will get as
minus 20.
Yes, correct. Okay, 5x square plus 10x minus 9. Differential you will get as 10x plus 10. X equal to 1, so 20 minus 20 voltmeter. Newton per coulomb or volt per meter, all are correct. Okay, so answer is option B, A. Is anybody having doubt regarding this one? Can we move to the next question? Somebody gave a thumbs down. Is it like no doubt or you understood? Okay. Next one. Two charges Q1 or Q2 are placed at 30 cm apart as shown in the figure. A third charge Q3 is moved along the arc of circle of 40 cm from C to D. Change in potential energy of the system is this. What is K? Okay. Now potential energy from here to here it is changing, right? At this point its total potential energy will be equal to potential of 1 into Q3 plus potential of 2 into Q3. This will be potential at C. How to find that? From A, distance is 40 centimeter from Q1. So K Q1 divided by 40 into 10 to the power minus 2. Or you can write 0.4 into Q3 plus K Q2 Q3 divided by, we have to find distance from here. Okay, this is 30, this is 40, this will be 50. Okay, so 50 into 10 to the power minus 2. This is potential at potential energy at C. Now potential energy at D will be same, potential due to 1 into Q3 plus potential due to Q3. Potential due to 1, it is still 40 centimeter distance. So it will be K Q1 Q3 by 40 into 10 power minus 2 plus distance between B and D is different now. It's 10 centimeter. So K Q2 Q3 divided by 10 into 10 power minus 2. Now to find potential difference, just find UD minus UC. Positive or negative value we don't have to see because all values are given as positive. So even if you get negative value, just take the magnitude. Okay, UD minus UC, this term will go. Then we will have K Q2 Q3 by 0.1 minus K Q2 Q3 by 0.5. K Q2 Q3 you can take outside. What? And it is working. Everybody can hear me, right?
Yes, ma'am.
Okay. So K into Q2 Q K Q2 Q3 we can take outside. 1 by 0.1 minus 1 by 0.5. 0.1 we can write as 1 by 10. So it will be 10 minus 0.5 1 by 2. So 10 minus 2, it will be equal to 8 K Q2 Q3. K will be 1 by 4 pi epsilon naught. So 8 Q2 Q3 by 4 pi epsilon naught. Comparing this, we will get K equal to 8 Q2. Somebody asked the second equation. Are you talking about this one? Second equation. Okay, this at point D, we have to find potential energy. So it will be potential due to 1 into Q3. Potential due to 1 Q1 will be K Q1 divided by distance between them, that is 40 centimeter. And again potential due to 2 will be from this distance, right? Initially it is this distance from D and C. Now B and D is this much distance only, 10 centimeter. Because it is given that AB is 30 centimeter, AD is 40 centimeter, which means BD will be 10 centimeter, like that. Okay. I hope everybody understood this question. Can we move on? Okay. Next one is a conducting spherical shell having inner radius A, outer radius B carries a net charge Q. If a point charge Q is placed at the center of the shell, then surface charge density of the outer shell. Okay. So spherical shell means this is vacant region, but the shell is thick. Okay. So this radius they have given A and this radius they have given B, right? Total charge Q is there already, okay, which means total charge Q is distributed all over the outer surface. Okay, Q is distributed all over the outer surface. Now extra charge Q is placed at the center. So at here I am placing Q, which means since it is a conductor, it will attract electrons, right? Since it's a plus charge, it will attract electrons here. This number of electrons will, total charge will be Q. Since electrons are separated, like it will repel positive charges also. It will repel same amount of positive charge to outside also. So it will be extra plus Q in the outside. So total charge outside will become Q plus Q. Okay. Now if you want to find charge density, it will be nothing but, I told you, total charge divided by volume. So Q plus Q, volume will be, since it is on the surface only, it will be divided by area. Okay. Surface charge density sigma, total Q by area, that will be Q plus Q divided by area of a sphere 4 pi r square, r is b, so b square. Answer. Okay, option C. Is this question clear for all? Okay, then we can move on to next question. So spherical portion has been removed from a solid sphere having a charge distributed uniformly in its volume. So in volume, if there is charge distributed, means it's a non-conducting sphere. The electric field inside the empty space, so this much space is cut from it. Okay, so what happens is that since charge was distributed in the volume and now there is a cut, means there are few charges here and more charges on this side, right? So electric field will be non-uniform. It will not be a uniform electric field inside this, and it will not be zero also. If it was exactly in the middle, equal charges are distributed around it, then electric field will be zero. So here electric field is non-zero, it is uniform. How it will be uniform is, I will tell you. Some charges are here, right? And same amount of charge will be near to it, and some charge will be away from it also. Since these charges are away from it, what happens is that their electric field is also less. These are near to it, its electric field will be more. So when you take on both sides, even though more charges are present on the upper side and less charge on the lower side, since because of distance difference, what will happen is it will be uniform electric field, but the electric field will not be zero inside. Okay, is that clear for all? In that case we can move on. Not understood. Okay, we might think that since charge is more here and less charge here, electric field will be more in the top side, electric field will be less in the bottom side. But no, it will not happen like that, because even though charges are less here, they are closer to the empty space. The charges on the upper side are like away from it. So when you take the total net sum of it, everywhere electric field will be same, value will be same. Okay, now is it clear? Okay. Next one, a negatively charged. This kind of questions you can hope, like mostly you will get. Okay, a negatively charged oil drop is prevented from falling under gravity. Applying a vertical electric field 100 volt per meter. If the mass of the drop is this, number of electrons carrying in the drop. Okay, so it is falling under gravity, so downward force is mg, but it is stopped with the electric field. So electric field in upward direction will cancel it out. So basically drop is falling with mg, upward force is electric field into q or electrostatic force. They are cancelling out, so we will get EQ is equal to mg, and Q can be written as Q equal to N into charge of electron. So our formula becomes NEE equal to mg. So N, number of electrons, will be equal to mg divided by E into E. Just substitute the values, you will get the answer. Yes, option D, correct. Okay. As you can see, most of the values will get cancelled out. Only 10 powers will remain. Then if you calculate that, you will get 10 to the power 12. Okay, like since we have only time for one question, let me select a good one. Okay. Okay, this one we can do. Two concentric conducting spherical shells of radius A1 and A2, A2 is bigger than A1, are charged to potential phi1 and phi2. Find the charge on inner shell. Okay, so two shells are there. It is having A1 radius, this is having A2 radius. This is having Q2 charge and this is having Q1 charge. Okay, now potential of bigger one, okay, potential of 2 we can find as potential due to this charge Q2. So K Q2 by A2. Okay, that is potential due to the bigger circle itself, bigger shell. Due to charge inside also there will be potential, right? So it will be added KQ1 by A2. This is A. Like inside, let's say assume like we are placing Q1 charge at a A2 distance, what will be potential? That is this equation. This is given as phi2. Okay. Next, phi1 equal to potential of the inner shell. First we have to find due to itself. So it will be KQ1 by A1. Now due to outer shell, okay, in outer shell, what is the potential inside due to the outer shell? That will be a constant value, right? That constant value is KQ2 by A2. So we get phi1 and phi2, potential of outer shell and potential of inner shell. We have to find Q1, right? So we can simply do phi2 minus phi1. If you do that, you can see KQ2 by A2 will get cancelled out. And you will have KQ1 by A2 minus KQ1 by A1. Now take Q1 common and do cross multiplication and you will get the final answer. Are you understanding this question properly? Okay. So you will get answer option A basically. Is it clear for all? Some more questions are added in the PDF. Please go through them, solve them. Okay, every day I am telling you guys, I don't know if you guys are solving or not. Please solve them. Like you need to practice at least an extra 10 questions every day. Okay, from the same chapter. Okay, if it's all good means you can leave. Join back for chemistry class at 12 o'clock. Thank you guys.